Yep. Welcome everyone to Rust Dublin, June remote meetup. Today we have a talk by Matthias Wahl about the Tremor event processing system. It's a cloud native computing foundation project. The title of the talk is Optimizing Tremor for Production and Usability. So if you will, take it away, Matthias.
And let's present. So my talk is optimizing Tremor for production and usability. And so I will not, like during the talk, I will not go too deep into like some Rust internals and specifics. It will be like more on what our development process is. I will talk a bit about why we chose Rust in the first place, because it brings lots of awesome properties that we harness. And yeah, we did lots of optimizing, and I will tell you stories about this, but I will not go too far into detail. We can do this afterwards, right? So I'm happy to do so, but don't be disappointed when I will not go to it. But it wouldn't be nonetheless very interesting, I hope. So I will give a talk, and then there will be some folk of Wayfair. So Tremor is started out as a project at Wayfair, and how they run it in production and what their experiences is. Like we actually have a Rust project in production and in like large scale, and it's maybe this is also interesting to you. So let's start right away. Our agenda is, I will give you an intro and what Tremor is. Maybe it's interesting for you, so you just get a really rough gist on what we're talking here. Then how we optimize for production. So this will touch the development process, some coding principles we use when we do Rust and why we chose Rust. And then the binary, how we optimize for performance. So what techniques do we use? What did we do? And then we also optimize for usability. So I will touch on hygienic errors and how to test and debug. So we try to be as, so like our main goals are being fast, have low resource consumption, and be nice and usable. So actually giving you a good time or like helping you along the way of developing Tremor applications. And then the most interesting part will be Tremor in production. So how is Tremor run in production at Wayfair, and what are the experiences with Tremor? So keeping me honest. So I'm a Tremor core team member, keeping me honest on what I'm telling you here. So let's go on a quick introduction. We have our GitHub repo here. I will share the slides in some form afterwards. So bear with me. So we have a Discord where we do where our community is, where we do our community stuff, where people are joining in, where we're discussing stuff or just chatting. Please join. It's fun. We have our site where we have our blog and docs, and we have an internal joke. I needed to put a snot badger here. So it's, yeah. We are a CNCF sandbox project, which we are quite proud of. So in this landscape image below, you can see us, our logo here in the streaming and messaging application domain. And we were born at Wayfair, and we are still sponsored by Wayfair. So they are paying us developing Tremor. So, and I'm going to touch on this special relationship with Wayfair. So a quick intro. So we are an event processing system, like there are many around. We are like, so the domains where we operate right now is logs and metrics, like shipping and forwarding and traffic shaping, logs metrics, everything in the observability domain, and search, or in general, you could say wherever you need traffic shaping, back pressure, rate limiting, or data distribution. These are the kind of domains where we operate. So we have a heavily optimized asynchronous runtime. So we use async std. Small is the actual runtime. We use libraries like SymD.json, accelerated JSON parsing. Tremor operates mostly on structured data like JSON, message pack, YAML, gRPC stuff, so protobufs, and so we need to operate inside Tremor on structured data. So, and this is like the core feature of the runtime. So we want to be as fast as possible, shoving events through, and yeah. So, and this is why we optimize so heavily. We developed event processing DSLs. So you write actually in our own little language, which is called like Trickle, where you write basically the pipeline, the event, we describe the event flow and the logic. And if you want to do some more detailed event processing, there's Tremor script, where you can match on, analyze structured data. For example, you get some open telemetry, JSON or gRPC, and then you need to check on some tags or rate limiting on some classes. This is what you can do. You can in place edit and update and enrich, and so everything event might or might not know from event processing systems. So our DSLs, they are interpreted at runtime. We run a small interpreter on that executes the script that you write on each event. So it's basically a kind of a reactive system from your point of view. So you react on events and then you execute your logic. And this is it. So, and you write, you will come to an example, but you write your application and it forms a directed acyclic graph of processing nodes. So basically think of branching and joining and alternatives and just sequences of operations. They are chained in a form of directed acyclic graph, and events will flow through it. And what we offer is efficient structural pattern matching operations. So if you like pattern matching, from Rust or Erlang or Scala, like there's some nice, so you can easily analyze and succinctly analyze your events. And yeah, Tremor script is an embedded functional programming language. To what extent it's functional, we can discuss, but it's a nice language. So if you write Tremor, you need to write a configuration. So Tremor is all about getting events in from somewhere, doing some logic on them, and putting them out. So input, computation, output. And you need to write a YAML right now. You define, so here, this is, we have an open telemetry on-ramp. This is the source for events that are injected into the engine, into the runtime, into the pipeline. It listens on port 4316, and it's decoding events as JSON. And then we have an off-ramp that goes to Elasticsearch, and in the binding, we put it all together with the pipeline. And then when we put this to a server, it will run and it will consume stuff from OpenTelemetry and write it to Elasticsearch. An actual event processing script that you would write looks like this. If you go from top to bottom, so first we define a script that we call it validate, and we match on the inside the script. We match on the event and check important field needs to be there. Some field is equal to has a value of a string called value. and must be a tags array that contains the string contains. And if it's fine, we just emit the event, then it goes through. Otherwise, we drop it. So like, just to give you an example of what you can do. Then we have a back pressure operator that if the downstream handling errors or exceeds the timeout, we apply some back pressure and to stop, to not overload the downstream system. We instantiate those, and then we apply the event routing with some SQL-like select statement, select event from input, from in into validate. And then so it first goes through the script, then it goes to the back pressure operator, and then it goes to out, which will then be sent to Elastic. So this is the gist of Tremor. It can be arbitrarily more complex. You can chain pipelines. You can have, for example, HTTP off-ramps where you send events as requests to a server, and then you react. And then the responses you will get back as evented to the pipeline. So you can build quite complex applications with Tremor. So, and now, how do we optimize for production? So first, the development process. So we were born to solve the problem of traffic shaping of logs and metrics at Wayfair, because I think during Cyber 5, everything exploded and it was not possible to see, actually see the logs and the current data of our system, the status of our system, because everything was overloaded, not only the system, but also the log and metrics pipelines. And for logs and metrics, you can actually throw away a sample and still have useful information, right? And this is what the initial use case for Tremor was. And Wayfair to this day is still a special customer for Tremor. So we have Wayfair internal support channels. We have regular office hours discussing Tremor roadmap and stakeholder requirements. So this is Wayfair internal stuff. But we are at the same time a CNCF open source project. So we are also kind of responsible to our community, right? So we need to balance the needs of Wayfair, which kind of are special to us, and also the needs of the open source community. So we offer open source office hours twice a month to the whole community. We have this Discord. We have an RFC process that is also valid, that we also go through for Wayfair. So it still needs to be. So we want to be as transparent as possible. So we adapted this from Rust actually. And so any change to the languages we develop, any change to runtime behavior should go, that is somehow substantial and not like a bug fix, should go through the RFC process. So, and how we optimize for production here is that, so we favor production value for our current users over our concept of a perfect Tremor. So if we can have a quick win and make the life easier or improve production for our users, and this is more valuable for us than, I don't know. So we wanted to introduce clustering into Tremor because it's super interesting, because we will integrate with Raft and the ring-based topology, and everything will be super complicated and horrible. We have set up some Jepsen tests and everything is awesome, but we needed to delay actually implementing this because Tremor, because there were other needs that we needed to be handled before that. And they are more important than what clustering will bring now, because there's no need for this, no outside need that very justifies this. Yeah. So it should be able to solve a real world problem that people come to us and want to solve. So right now we are heavily improving our guaranteed delivery semantics in Tremor. So we have some acknowledge and fail mechanism. So where, for example, if you input stuff from Kafka and you put it out to Elastic, and then it will only be, the offset will only be committed to Kafka when it was sent to, when it reported as successfully sent via Elastic. So, and this is needed to be done first. So now maybe the interesting part. Why did we choose Rust? I mean, it's, you might know it's low resource usage. You can be very low level. So we do some nice tricks we weren't able to do, and all this safely. So we never had, until now, we never had any production outage or any incident that was related to Tremor misbehaving or Tremor seg faulting or anything. So it's behaving nicely, and thanks to Tremor, thanks to Rust. So our Rust coding practices are maybe, I don't know, like stock Rust, good Rust behavior. It's nothing surprising. We avoid panicking constructs because we run a production binary. We do obey Clippy and pedantic mode. We do Rust format. We require Rust format. Actually, so maybe, so Clippy is super annoying, but it's actually super helpful. Like when we introduced pedantic mode, I think we had a solid 3% performance increase in our benchmarks. So it's so obeying Clippy tips is actually worthwhile. So we try to have a good test coverage. Test coverage is controversial, but we try to be good here. Like we are above 80%. Yeah. So we use fuzz and property-based testing. We use prop test. We use Erlang quick check, EQC. So we test our language implementation against some randomized input to see if it executes correctly. We do some useful logging just for debugging production systems, and we have like an error strategy, like what errors actually fatal, then join, and we have like most of the code we write is actually handling errors correctly, and like can we recover from this, or should it like is it war? Just log it and we cannot do anything. So we try to be rigorous here because it's in production. So for optimization purposes, we try to avoid clone wherever possible. So if you try to be zero copy in Rust and avoiding clone, like for example, taking the event byte vector and extract the values from it, for example, extracting the JSON strings and all of that, then you know you are bitten by lifetimes, and dragging them through to the whole system really is super, can quickly become super annoying. So I'm still, I didn't make my peace with lifetimes yet. So we do clone at some point, but it's always kind of in reviews. It like we need to justify why we do the clone and not go like try to avoid it. So we need to try to avoid it at least. And yeah, like also obviously we spare a allocation. We use all those data structures with capacity, so to allocate some big chunk up front and then fill it. Just like this is no magic, everybody knows. And because this is all in terms of saving on allocations, we use Microsoft's SN malloc as our default allocator, which is an allocator that is based on message passing. So it's written in C++, and there's a SNMalloc port. And for our use case, where like you have an event is coming in, it's handled with a task on this one thread, then it's passed through the pipeline to multiple threads, and it's usually deallocated on another thread. So you have basically you have the topology of where stuff is allocated and where it's deallocated. So we really benefit from SNMalloc here because it fits our use case. We used memalloc and you know all the others. SNMalloc is really nice for what we do, and give it a try. Yes. So when we optimize for performance, so we do regular detailed performance analysis. Basically, for example, our pull request template contains a section on like what is the performance impact of this change. So we need to justify and we need to check what is the impact. We do flamegraphs to analyze some stuff. Yeah, we do tidy up the hot path. So our hot path is really our like sacred piece of code. And if we change, we have it commented all over the place. This is the hot path. Be careful. Test, and benchmark. And so this one is really clean, really optimized. And one experience is with regards to performance. Usually your intuition is just wrong, and what you think works or improves performance actually doesn't have such a great impact, and actually like tiny stuff you wouldn't think impacts performance does to a like big degree. And we do benchmark regularly. So we are in the process of setting up a CI benchmarking system that benchmarks every release and every commit, so you can track the behavior. The graph below here is from a real world, some where we measured the latency of events, and it's in nanoseconds. This is just some output. We don't like I don't go into interpreting this now, but so we compare those. This is just example output to give you some illustration. And what we also regularly do, we look at common usages and optimize for those. So for example, in our, I think it's metrics pipelines at Wayfair, we have huge match statements on, like, because we need to categorize all the events coming in. And like we optimized for those huge match statements, and they were, I think, by a factor of 2 times faster afterwards. So this is how we optimize the performance of production systems. So I mentioned already we use the async runtime and async runtime. So everything is async based on small or the async std. And like we chose async std and small over all the other runtimes. Like a year ago, we tested like roughly and benchmarked everything, and this was the fastest. I think we should redo them. There are new ones around, but so we switched from a thread-based model, like for example, an on-ramp where we consume from OpenTelemetry, and an off-ramp where we write to Elastic is run in its own thread. So now we use tasks for this with the async runtime, and it's much better scalable. You can run multiple pipelines in one Tremor instance, and it's much better. So we have a nice blog post about this. If this is interesting to you, go to our blog. Every part of a Tremor runtime is communicating via async channel. So we have, this brings us, it's like, you can think of it like a bit like an actor system or something, where we have every instance, like say a pipeline or an on-ramp is running in its own task, and it's only running stuff sequentially, and we can leverage some properties that this has, and then it's communicating over channels and to others. Like everything is is modeled after this. So I in my spare time I did I maintain the Pony language. Heinz, another member, has a nice Erlang background. Darach also has some Pony background. So it's we kind of are like this is somehow a theme for us. It works quite well here. So some more optimizing tricks. We do some hashing tricks. We use the half-bound hash map, which uses a back actually with linear probing for small sizes and dynamically switches to Swiss table. So what's now in standard or in STD or like which was hash brown or is still hash brown, but it's uses this one for bigger tables. So we also optimize. So when we have use cases where we know hashes and where we very often access known keys, we can optimize for those by using a hash function that is creating the same hashes, and then we can spare computing the hashes, and this can really bump us up like 5 to 10%. Like if this is on the hot path, then it's really worth doing some such tricks. And the biggest one I think we do, and the nicest one is SIMD-JSON. It's a Rust implementation of Lemir's C++ SIMD-JSON project. So it uses SIMD instructions and big vectors to accelerate JSON parsing, which is not obvious how to get SIMD and JSON parsing together. But they use some really nice tricks. And also Rust is a really wonderful language if you want to go into the low-level platform-specific SIMD stuff. So this is also like where Rust really shines. So this is a line from our cargo config. We always enable those target features, and if like you should run Tremor on a machine that supports any of those, AVX, AVX2, SSE42. You can also run it on ARM. ARM has Neon, but yeah, you need nightly. So I think Tremor doesn't run on ARM right now, but it will very soon. So yeah. So this was the performance stuff. We can get into this later and in more detail if you want. But now for usability, which is also like a really important topic to us. So we want to have hygienic errors wherever possible. So we want to have helpful errors that point you to where stuff went wrong, and B, help you out. Like error reports are like, they need to be helpful. They need to be, so you need to you need to see what's wrong, and you need to see how to fix it. And what we have is, when we load scripts, we interpret them and construct an AST and basically some format that the interpreter can run. And we emit errors here. So when we load your scripts, and we also have hygienic errors at one time. So below here you have like I just made a screenshot here. I was running a script, and it gave me 2 warnings on, I used a tumbling window in a kind of dangerous fashion, possibly dangerous fashion. I used a aggregation function that's possibly very expensive memory-wise, and I got warnings, nice. So I knew, hey, you do something that's bit dangerous. And then I input some event, like some empty JSON that is not expected by my application, and so it's throwing an error here and telling me, hey, trying to access a non-existing key tag. So yeah, this is what we are trying to do, and if we can get better at errors, this is always helpful. I mean, we developed our own language, so we are also responsible on making it nicer and for you. So we developed also, like previously everything was basically YAML, and now we only have a small part that's YAML, and we are in the phase of killing that YAML and writing another language for replacing that YAML. And why we go with all those our own languages that you need to learn and that you need to look up when writing is we can provide you those nice, really nice, helpful error messages. And we have some opportunities for optimization, some custom optimizations, and there, yeah. So, but like from a Tremor developer point of view, what we need to do for this is we need to track the source file and positions in the interpreter or in the actual in the actual AST that we then interpret. So we kind of have to use self-referential structs because we need to basically store the actual script part, the AST, and have the interpretable, executable expression be reference to this. So if you ever dealt with self-referential structs, fun. Yeah, this is the pain we go through for making Tremor usable. So we also have a Tremor language server that you can simply install with Cargo. And we have a Tremor VS Code extension, for example, that is using this Tremor language server. So you can also use Vim or whatever Emacs. And so we have, we go through lots of effort to make it usable for you. And then on top, you can run your application or logic against synthetic events to do some preliminary testing, to check if it works as it should. You can input some events from a file. You can input something from the terminal or from stdin. You can run unit tests for your scripts. So if you write some functions for, I don't know, transforming some JSON format, or I don't know, calculating some difficult math in Tremor script, then you can test it and have some unit tests verify that stuff actually works. We have a course on, we have some courseware around on testing, so try this. It will go into detail how to set stuff up. You can also integration test, not only tiny scripts, but your whole Tremor query where you have those select statements and everything. And you kind of play this against some fake on-ramps, like loading your JSON from a file and outputting it to std out and then asserting on the output. And so this is all built into Tremor, and you can use this. You can also build graphics, a dot graph of your pipeline. So like, it looks really wonderful. You can debug into the AST if you're into something like this. So we, like develop your Tremor application and make sure it works for yourself. So now let's go into Tremor for production. And I think it's Naga who's going to talk to you about how Tremor is used in logging and metrics. I will be your slide machine, sorry. I will need to mute myself. One moment. Yep. Okay.
Thanks, Matthias. Good evening, everyone. I'm Naga from Wafer's observability team. And so today I would like to share some of our experience with Tremor and how Tremor helped us to transform some of our core monitoring logs from various sources and then finally ingest into Elasticsearch. So if we go into the logging slide, okay, this is our current setup model or whatever the key points that we have. We have heterogeneous data sources. Some applications writes their logs to file. Some of them directly post into socket, to TCP, UDP, and then some applications directly post into Kafka, and some of them uses FileBeat. So we have pretty much all the combinations of data sources. And Tremor helps us in the various aspects, like to collect the logs, rate limit them, and then transform them into a proper format, what is suitable into our Elastic format, JSON format, and then finally ingest into it. And with all those the heterogeneous data sources, Tremor just acts as our one-stop shop. So Tremor provides all handy on-ramps for pretty much all our use cases. And then we were able to cherry pick all the configurations, and then boom, we were able to connect to them and then extract the messages from all those sources. The very beauty of Tremor, what we leverage a lot is the monitoring of the monitoring. So even when the pipelines goes, even without any extra effort, Tremor itself gives its own insight, like how much data has been digested into the pipeline, how much has been processed, and for any of the rate limiting reasons, if it needs to drop some of the data, how much has been dropped, and finally how much has been emitted into our off ramp. So pretty much all the metrics has been collected, and then that metrics is also we are ingesting into our InfluxDB for our further triaging and then monitoring of monitoring. And in our production setup, we pretty much collect logs from all the applications deployed in all our 5 collocations. And then we have 500 plus Tremor nodes for all our collection, transformation, and then ingestion layer. And our throughput goes anywhere between 100K, it's still increasing. So 100K messages per second. At that rate, we are processing it today. So all those features are coming to us in a very handy packed manner. And then if there are any issues, if there are any feature requests are needed, the turnaround time is also very quick. So we will, since we are internal, we go to the teams, we tell, just put them a request that, hey, we are working on this feature, we want blah, blah, blah in the next release. Then they evaluate it, they go through the process, and then within the short span of times, we will be able to get all those features back into the new versions of it. And I would like to share one of the some of the key values that we gained in our very recent migrations. Most of the times as we migrate into Tremor, the performance benefit is very significant. We were visibly able to see that. Few years back, most of our transformations was handled by Logstash. Logs collections and even processing everything was handled by Logstash, which was not which was working to address our needs. But as and when we moved to Tremor, immediately we were able to see great performance gain, and we were able to cut down our CPU cost by 50%. Straight away, we were able to cut it once we move our use cases to Tremor. Recently, we're also migrated. Most of our use cases have been already migrated to Tremor. We still have few legacy cases here and there. Recently, a few weeks back, we did a migration for one of our component, and then earlier we had some fallbacks on the Logstash side. It does support rate limiting, but it does not have features like set it up at the dimension level. So whatever the chart that you see on the right hand side, it's just our log count from our Kubernetes namespaces. So earlier, if some of the Kubernetes namespaces is abusing the logs, they used to take a big chunk of our rate limit quota, and then other namespaces logs would not be end up in our Elasticsearch cluster. And we moved to Tremor. We set up the dimension-based rate limiting. So here the dimension is namespace. So for every dimensions, for every namespace, we were able to allocate what rate we wanted to set. So as this is the result that you see, for every namespace, we were able to give equal amount of quota, and that gives us a great benefit from a user perspective, and we were able to cut down. Basically, our logs got much better from the usability perspective. So on the next slide, I have some details on how we are processing our metrics. Matthias, if you could go to the next slide, we have some details on. Yep. So again, for the metrics, we have a very similar setup. We have somewhere close to 700 nodes in our production footprint. That's our footprint on GCP. And again, we have heterogeneous data sources. Here, apart from what we are doing in logging side, for the metrics, we are also doing aggregations and downsampling. So the rate limiting is very heavy in terms of metrics, and the amount of data that we process also very heavy. Since we kind of process 4 million metrics per second, which is way higher than what we handle in logs, of course. And at the end of the pipelines, we also generate our aggregated metrics like 5 minutes roll up, 10 minutes roll up, 1 hour roll up. So pretty much in all our use cases, we are able to leverage Tremor, and of course, it's very stable in productions, and we're happy about that. Thanks, Matthias. I think that concludes our metrics and loggings.
Thank you, Naga. Now we have Negos from our Kubernetes team. Sorry, let me.
Okay.
Yeah.
Okay, you can leave it on the diagram. Thank you. Good evening, everyone. I'm Negos. I'm part of the Kubernetes platform team at Wayfair. I will just show a few examples how we utilize Tremor for parsing some kinds of logs inside the Kubernetes platform. So Matthias, if you can switch to the next slide, please. Thanks. Before, there are like multiple logs and that we can collect from the Kubernetes platform, and there are like multiple tools already, like Vector, like you can use FileBeat or whatever. For our workloads, FileBeat was not able to handle all those logs. For example, during the peak hours on the peak ingress nodes, we are sharing like 100K thousands of the logs, and we had issues with file rotation and FileBeat, and similar thing is happening on the worker nodes, where we have a lot of Docker containers running, and FileBeat, for example, is not able to perform any rate limiting. And for example, if you look in the ingress node, we can Nginx ingress support like 2 modes. You can write logs directly to the log file, or you can send it to the remote syslog server. And for example, we decide to switch to send logs to the rsyslog servers, where Tremor on ramp is acting actually as rsyslog server. We use text processor to parse those events, and then we use Tremor script, as Matthias explained. So utilizing easily logstash dissect plugin inside the Tremor script. There are like multiple plugins, and is supported inside the Tremor. We can easily convert text file like from the rsyslog default rsyslog format to the JSON. We can easily append some metadata, for example, node metadata, cluster details that we can use later for filtering. The similar thing we did for the ModSec web application firewall logs. So we have like small Golang application that is parsing those logs and sending them to another on-ramp on the Tremor. There's another script specific for those kind of logs. And there we also parse them and send to the Kafka pipeline. For example, here with Tremor, we can easily use, which is great, you can easily use multiple dimensions and classes for the rate limiting. So you can say, for example, not only per namespace, I want like logs per namespace, per host name, per container or whatever. So you can have multiple dimensions and you can fine grain the logs that will end up in the system. Probably access logs are not that important. They can be used for the debugging stuff. But for example, error logs, Nginx doesn't support JSON, so it will just throw a text file with a lot of errors. And if you push that to the pipeline, I mean, there will be some issues. So we can easily can catch this event on the Tremor, extract what we need, format this as a JSON, and ship it to the logging pipeline. Another use case is we're using FileBeat, for example, on the worker nodes. But we had a lot of issues, performance issues, even if you cannot run a lot of pods on the one worker node. We were not happy with FileBeat. This is still in the POC, but we decided to use Vector. It's written in the Rust as well. It has way better performances. And as Naga said, so they already have limitation on the pipeline side. But if you don't have limitation on the worker node, all this events traffic needs to be sent somewhere to the pipeline. So it usually generates more costs because you need more resources. So we can actually apply the rate limiting per namespace or per multiple dimensions on the worker node. And one more thing is we're utilizing Tremor as well for shipping Kubernetes events. There is the small controller operator written by OpsGenius. So it pulls the events and ships them to the Tremor. So on the Tremor, we as well parse them, make them valid JSON, append some metadata that we need, and organize them. So, example, you can get like you can drop like half of the event if you don't need it, or you can organize it in the structure that your logging pipeline is expecting. And the great thing with Tremor is like it requires a very small amount of the resources, and that's the great. And I think that most powerful thing from our side is that you can use script. And you can write in the script whatever you want. So that's the very powerful. So that's, I think, everything I have.
Thank you, Nikos. And this is it from our side. And if you have any questions, let's go into the Q&A and into the chit chat. So I think there was something going on already on the chat, and Darach was helpfully answering. And so can we go into detail with you? Any questions?
Thanks for the talk, first off. You mentioned that there were a bunch of optimizations you thought would pan out that didn't, and that you were kind of surprised by performance characteristics sometimes.
Yeah.
Were there any good examples of optimizations you made that really surprised you by how much they affected things?
Yeah, so I never thought that, for like just personally, I never thought that switching the allocator to SMalloc would have such a great impact, but it. I don't fully understand why also yet, but I just think it just matches our pattern of allocating events, and on the one hand of our pipeline, and then dropping them on the other side. And this just is what this is the kind of payloads SMalloc was built and optimized for. So this one, I recently just changed our data structures for basically event tracking. So we track, so when an event flows through our system, we track if it's if it was caused by other events, or if it was, for example, if you do we support tilt frames, so you can window basically by sizes, and you can build tilt frames like Naga told us about, like 1 minute, 1 second, 1 minute, 1 hour roll-ups. You can do this with Windows, and so those windowed events, those aggregated events, they are caused by those other events. And we use this for tracking, and I changed the data structure for this tracking to avoid allocations in the normal case. And I thought, yeah, we save an allocation, we save, we do a lot less when cloning, and yeah, so everything will be nicer and more fun. But it actually just had a very, very small effect. And yeah, this one. And then there is, so we use SIMD JSON for parsing. Like it's like 2 times faster than the fastest, like the C++, 2 times faster than the fastest, like Rapid JSON or something other JSON parser. And we are like when in benchmarks that the third people did, we were also like up to 2 times faster when parsing some common like some big files with lots of JSON inside. And then someone benchmarked, for example, very small JSON files, and there we are just like 50%. Like we're a bit slower than third, for example. So it's the surprising thing comes from the actual from setting, like how to, like you will see surprising results if you slightly differ how you set up your benchmark, right? And what actual case you are measuring. So in our case, we stream JSON through, and we have like the usual stuff we handle right now, or we handle a reasonably sized JSON. So it's not like tiny JSON documents. And so if they have some size, it actually SIMD JSON pays off. We do some more optimizations by reusing the buffers we use for temporary stuff, like copying. Like we in JSON, you sometimes need to de-escape strings, and then for stuff like this we reuse JSON. So we have still some really good performance also on smaller ones. So because of how we use it, yeah.
Nice one. That's really interesting. Thanks.
Yeah. It's a rabbit hole. Right? It really is, because you can like it's you. Yeah. So you build up a hypothesis. So you observe some like stuff is slow, or throughput is not where we want it to be, and then we go. You build up a hypothesis and try to verify it with changing the knobs, and then you might see that this is not. So your actual hypothesis was wrong, and this is how we usually do more iterations and on this.
Nice one. If I can help for like one more question.
Yes.
So you're kind of basically like you're running async, right? Fully.
Yeah.
What were you using to generate those flame graphs then, or what are you using to kind of track? Is it like a span tool, or?
We use it's called flamegraph, cargo flamegraph, I think. Wait, I have it somewhere here. think I need to open it.
Yeah,
This tool,
it's Cargo Flamegraph. I think, was that the one that John Gings had ported across? Because yeah, that rings a bell.
Yeah.
All right,
yeah, it's like, this is John. Yeah,
cool.
yeah, it uses Inferno. Yeah,
Perfect. Yeah, that makes sense. Cheers.
yeah. Maybe so to get you familiar. So this is our Tremor documentation. I hope you can see this.
Mm-hmm.
And so we have on-ramp that is a REST on-ramp that is that supports HTTP 1.1, and it will try to deserialize the response based on content type, and will give you request metadata with the event that you can act upon. And then you can also send events back to this on-ramp and basically respond. So basically implement a full HTTP server in Tremor. This is what we did. And we also used a off-ramp that's called KV, that is a persistent key value store, where you basically send events formatted as KV put or get commands, and you get the answer, so the value out. And but we have many more. We have Kafka, NATS, Postgres, TCP, UDP, WebSockets, AMQ. We recently got some AMQP. We do have codecs for handling like some most common formats, including syslog. We have preprocessor and post-processors for doing compression, decompression, line splitting, base 64, length prefix decoding, and stuff. And then we have our really detailed references for our languages. Basically, here with some railroad diagrams for grammar, and this is some big explanation on select statements and how to use them, and grouping. And it's really so I think we have a lot of resources to get you started. There's Tremor script for example, you can match on complex patterns here for stuff like textual and structured data. We use for, like, if you ever want to implement a language in Rust, which we did, we used LRPOP, so LalaPOP, for the grammar. It's basically a grammar DSL. And there is, we wrote our own Lexa, which you shouldn't, which no one should. There is a crate called Logos. We want to try and replace our awful own implementation of this. So yeah, we are kind of into languages and stuff. That's why we went this way. Okay.
Thank you so much, Matthias and gang.
Thank you.
A very, very interesting talk.
I will share the slides with you all. I don't have them published anywhere, but I will do this this evening.
Great. Okay, and we'll publicize them through Rust Dublin's Twitter account. So, and we'll upload the video usually within about a week. And of course, we're always looking for interesting talks about Rust and people's experience. So, anyone, if you've got like a useful learning experience you'd like to talk about with respect to Rust, like a usual even or an unusual use case, success stories, dismal failure story. No, not really. Yeah, anything that has to do with Rust, we would like to hear from you, and we will make you famous, or YouTube famous anyway. That's it, I think. And we shall see you in July for our next remote meetup.